My name is Oskar Skean, and today I'll be talking about emergent abilities and foundation models, so kind of finding their hidden talents. Um, so yeah, we just had the little about me, so I won't repeat myself here. I will say a lot of my work is pretty domain agnostic, so I've worked a lot with text data, tabular data, images, and just all sorts of data, and these kinds of techniques like information theory that I look at for understanding models. It's all very general, and especially in more recent years, it seems like different modalities, like different architectures, are all kind of converging to the same kind of findings, like the same architectures and same styles of foundation models. So the takeaways from this talk, I hope, are very general and can be applied to whatever your problem domain may be. So the key takeaways for this talk, so we'll talk about like how emergent model capabilities are found and measured. We'll talk about how self-supervised pre-training, which is the most common form of pre-training these days, can lead to general representations that are applicable to many tasks. And lastly, we'll talk about how information theory can be used to help uncover internal model dynamics and understand how information is flowing in large models. So starting with what is emergence? So let's align on one definition, not the only definition, because you could have many different definitions of this. But this definition was proposed in 2022 by Wei et al. So an ability is emergent if it is present in large models but not present in smaller models. And what that might look like is something like this. So here's a couple tasks taken from that paper Wei et al. So we have modular arithmetic and IPA transliteration, which is the International Phonetic Alphabet. And so this model is pre-trained on like text next token prediction. So this is a language model, and we're applying it to these different tasks. And we'll see on the x-axis is like model scale, which is the number of training floating point operations in this case. And we'll see that like it's kind of performing at random, and then all of a sudden it jumps up and it starts getting very good. And this phenomenon was kind of the first early look in emergent capabilities, like this sudden jump. Like why is this large model suddenly capable of something that the smaller models aren't? And we can also see this not just with training flops, which is one way to measure scale. We can also see it with model parameters. So just imagine that we're scaling up the model, adding more layers or wider layers, and we'll see a similar jump as we are increasing the number of parameters. So we see that with the chinchilla and gopher models here. So as we 10x the parameters from 1 billion to 10 billion, it's still about the same, but 10xing from 10 billion to 100 billion, there's a sudden jump, and a pretty substantial jump on the MMLU benchmark tasks here. I will say this definition isn't perfect, and a lot of it depends on how you are measuring accuracy in your models. So you can imagine, like for this modular arithmetic problem, or even like let's say you're doing multiple choice or exact string matching, it's not a continuous accuracy metric. It's either right or it's wrong. There's no like in between. So in the case of exact string match, it's only right if every single character of your output matches your baseline that you're measuring for. And so this discontinuous accuracy metric can cause the jump a little bit. So like that previous big jump that we saw where it was, performing at random and then all of a sudden it gets very good. If we make the scores continuous, so going from this discrete accuracy measurement to some continuous one, like a Breyer score here shown on the right, it actually kind of linearizes the performance as you increase with scale. So this is from a great paper, Schaefer et al., which was essentially emergent phenomena. It was called Emergent Abilities or a Mirage, which I think is a bit of a strong title, but it's essentially saying that the way you measure accuracy matters a lot. But we still see here, even with this continuous score, that as we increase scale, the models are getting better and better and better, which makes sense. So maybe a slightly better definition or maybe one that's more general, that I prefer, is that an ability is emergent if the model was not explicitly trained for it. And the remainder of this talk will be centered around this definition. So like this notion of continuous and discrete accuracy doesn't really pop up in this new definition. And so we'll take a look at envision models and language models, kind of situations where this arises. And this definition is a little bit more exciting as well because it lets you like find new use cases for an off-the-shelf model. Like let's say I download some open source model that was trained for some particular task. Like maybe I can find other situations, or maybe like situations that are important for my work that the model can be applied to. And looking at emergent capabilities in these models lets us know like what they're actually capable of, but also it helps shed light on the training dynamics of the model. Like especially like if you're observing the model during training, can you observe these things, these new capabilities arising, and like what does that tell you about the training process? So it's a very it helps open the black box to these models, so to speak. So it's a very powerful thing to look for. So we'll now jump into looking at some examples of emergent phenomena in vision models. And so as I mentioned earlier, so modern state-of-the-art backbones in vision, but also in general for language and most tasks these days, are trained with a self-supervised loss. So what this means is the labels that you're training with are derived from the data itself and not from some classification level. Like if you're training on images, you're not training in the traditional way of like this image is a cat and like training for that label, that specific classification label. You're deriving the labels directly from the data, such as augmentation and variance, which we'll talk about in a second. And this lets you scale to much larger data sets because you're not constrained by these manual labels. So emergent capabilities and self-supervised models. So if you're training on like some general loss, you'll often find that your model is now capable, like after the fact, of like segmentation, depth estimation, surface normal estimation, and also classification. So the single model is capable of doing all of these different things. And so with that in mind, we'll do a walkthrough of a research timeline of the DINO models, which is like a very great vision backbone out of Meta. And we'll talk about just how emergent capabilities for the DINO models were found and discovered throughout the years. So starting with DINO version 1, which came out in 2021. So this paper was actually called Emerging Properties and Self-Supervised Vision Transformers. So even back then, they were training this with the intention of understanding what models were capable of. So this DINO paper introduced a new self-supervised vision loss for training vision backbones based on knowledge distillation. So the details are a bit technical, but essentially you have a student model and a teacher model shown on the right, and you have some input image X that you augment a couple times. So you add some noise to it, maybe you rotate it, but you have like some augmentation X1 and some augmentation X2. And the idea is that the representations from the student and the teacher on this image will match. So the outputs from these networks will be invariant to the augmentation. And so the network will learn semantic features rather than stylistic or like image specific features like the orientation or the noise. And this flavor of loss function, there's probably dozens of loss functions like this these days. And this knowledge distillation is just one way to do it. But if you do it like this, something that's very cool is that if you look at the actual attention maps of the network, so these are vision transformers trained with, attention, the attention mechanism, the network learns to identify entire objects. So you can visualize you can visualize what the network is paying attention to for a particular object, and nothing in the training loss was telling it to do this. but you're just looking at what the network is paying attention to. And so this is what they called emergent semantic segmentation. So, like for instance, you can like highlight a toothbrush, and the model has no concept of what a toothbrush is. It doesn't know that it's used for brushing teeth. Like this is a vision model, but it understands that it's a whole object. There's a follow-up shortly after, uh, which was deep spectral methods, which is taking the off-the-shelf DINO model and using the representations, um, and not doing any training, but doing some post-processing on the representations by doing spectral clustering, and you can get even cleaner segmentation maps. So instead of looking at the visual attention like we just saw, this paper looks at the spectral clustering of the representations of the patch level features. And what this does is it gives you cleaner segmentation maps, and it gives you multiple objects. So now in the top, we have someone riding a horse, and so you can highlight the horse, you can highlight the obstacle it's jumping over, you can highlight the little sign. Whenever I show this paper to people, I always like the bottom row here where it shows the sheep that's behind the fence. And it's just so interesting that like the fence is overlapping the sheep, but the model is still able to like cleanly segment those two things. And so I'll emphasize like this is taking an off-the-shelf model, not like fine-tuning it or training it at all, to get these special maps. It's like just applying spectral clustering to these representations, and you get these really great results. And you can apply this to like spectral segmentation tasks now, or semantic clustering tasks, which was not, I'll emphasize, what the model was trained to do. So moving forward 1 year in the future, so now it's 2023, and we're looking at DINO v2. So this is learning robust visual features without supervision. So this paper, it's a very good paper. It's more of an incremental improvement over DINO v1 in some ways, in the sense that it's mostly engineering improvements. So they've improved the data curation, they've made training more efficient. The code is like very clean and public. All of these models are open source, by the way. And they also did some slight tweaks to the self-supervised learning losses. Like they combined a couple different loss functions together to train the model so that it learns like patch level features and also global image level features, which makes even more powerful models, it turns out. And now, and they explicitly were looking at even more emergent tasks. So we have segmentation, we have clustering, we have depth estimation now, where the model can learn, or it can kind of predict like the depth of objects in the image, and also just general classification tasks. And there's many more discussed in the paper as well. But it's like kind of the capabilities of the models, over the years are just getting more and more visible. Like people are applying these models to more things. And so stepping 1 year further in the future, so that now it's 2025, where it's 2 weeks ago, where this paper just came out, DINO v3. It introduced a technique called gram anchoring, which helps prevent attention maps from degrading over long training periods, that's a problem that's discussed pretty frequently in the literature. And so this paper came up with some remediations for this. And now there's like dozens of tasks explored in this paper. And this paper just came out 2 weeks ago, so I didn't look at them all yet. So one of the figures that stuck out to me was even cleaner segmentation maps. So because of this gram anchoring, the model has like much cleaner attention masks. And so the middle row is kind of like a DINO v2 attention masks, like the semantic. But if you do this gram anchoring, it looks at like the bottom, and it's very, very clean semantic segmentation maps. So we have the flower highlighted, or the herd of geese. Or the seals on the beach. And like who knows the limit of the tasks you could apply this to. Like dozens of tasks explored in the paper, lots of benchmarks, all trained from the self-supervised loss. So it's very general representations. And I will say the DINO series has also been applied to things like canopy height estimation. So if you have like an aerial view satellite image, you can like estimate the canopy height. You can also apply DINO to like medical images. So like these are slightly out of distribution tasks, right? Like the images above are like kind of object centric images, but it's learning very strong visual features that are applicable to non-object centric images like satellite images and so on. So now we'll take a little shift over to the language model world, and we'll tie it back to vision kind of near the end. So looking at emergent phenomena and language models. So we'll now be discussing my work. So I'll be discussing this paper in particular layer by layer and covering hidden representations in language models. So this was just published at ICML 2025 as an oral presentation. And the one-line takeaway of this paper is like we're examining internal model behaviors that emerge naturally over the course of training. So not necessarily looking at emergent capabilities, but emergent training dynamics and like what is going on inside the model without us explicitly telling it to happen. So these are some of my co-authors. So this was like a very general, there's co-authors from all over the world, three different continents, several different countries, a lot of different institutions. We collaborated online, and yeah, just a very great project and great co-authors to work with. So just an overview of the work. So this work challenges some common assumptions that a lot of people have about modern machine learning. So a lot of people, when they do, let's say they take an off-the-shelf model and want to apply it to their task, or maybe they'll train their own model. There's this common assumption that final layers always give the best embeddings. That's just the way machine learning is practiced. So you'll take an off-the-shelf model, do a forward pass, and take the outputs. And there's a complementary assumption that the middle layers are useless for downstream tasks, or it's at least hard to apply them. The reality is that intermediate layers often outperform final layers. And we'll see that, and we'll have some explanations for why that might be. So this work, we look at specifically the embeddings of intermediate layers, and we're looking at downstream tasks, which are embedding tasks. So we'll take, for instance, we'll take prompts and classify the semantic, like happy or sad response of the prompt. So like, let's say it's an Amazon review. Are the customers happy with their product or not? So we can classify that from the prompt as an example. So we also do rigorous empirical testing across model architectures, scales, and different tasks and modalities. And we also introduce a theoretical toolkit of evaluation metrics to help understand why intermediate layers are strong, and why these internal phenomena might be occurring. So the benchmarks we're looking at are primarily what's called the massive text embedding benchmark. So it's a state-of-the-art benchmark from Hugging Face, where we look at 32 diverse tasks spanning 5 different domains like clustering or re-ranking or classification, as I mentioned. And we probe every single model layer on these tasks. So let's say a model has 30 layers. So we're doing 30 times 32 evaluations. So it's quite a bit of compute. But luckily, we're not training anything. We're just doing inference. So it's, fairly quick. And our goal, very simply, is to find which layers create the best embeddings. And we can jump straight to the one of the main graphs of the paper, which is the y-axis is your average accuracy on these tasks, and the x-axis is your layer depth. So at 100%, you're at the end of the model. At 0%, that's the very first layer. And these models have different number of layers, which is why it's as a percentage on the x-axis instead of just the layer number. But we can see that across these 3 different models, The middle layers are quite a bit better than the final layers, and these tasks are kind of zero-shot tasks. So the model wasn't trained for these. Um, and you could probably improve the final layer performance by doing fine tuning. But the idea is just to take a model, download the model, and apply it to your task directly. Like very easy pipeline that most people would want to do. And if you just do this easy thing, you can get like a 15 or 20% boost by using the intermediate layers on with certain models. And so I'll also emphasize that these are three different model families. So Pythia is a next token prediction trained model, very similar to like GPT style models. They're also called decoder only models. BERT is a mask language modeling model. So these are the encoder only models where you mask out some words and try to predict the words from the surrounding context during pre-training. And Mamba is also trained with next token prediction, but this is not a transformer. This is a state space model. So three different model families shown here, and across the board we're seeing this behavior of peak performance in the intermediate layers. Our experimental pipeline. So going forward to like understanding why is this happening. So our experimental pipeline for looking at these intermediate layers. So we take a prompt. We this prompt has n tokens, and we pass it through the first k layers of the model, and now we have n embeddings at that kth layer. So we have n like vectors, n token embeddings, and using these embeddings, we can apply many different evaluation metrics. So as I mentioned at the beginning, like my background is more information theoretic and applying information theory to understanding these models. So we have quite a few of these kinds of metrics in the paper, understanding the information content of these embeddings. We can also look at augmentation invariance, which is looking at how robust the model is at understanding things like typos in the prompt. Like if you add typos or random words and so on, how does the model understand these? Yeah, and so information theoretic is understanding how much data is preserved. Augmentation invariance is how stable are the representations to augmentations like typos or new words. And the fifth or a third metric, curvature, is understanding the shape of the data. So how curved is the embedding space, and how kind of if it's very smooth, that might imply that the model is understanding pretty well. But if the manifold is very jagged and curved, then the model might be struggling a bit for understanding the prompt. So these three different metrics, these three different metric families, each kind of impart a different understanding of the model behavior. So we'll look a little bit at the information theoretic metric. So this one, as I said, is understanding how much data is in the embeddings. So one we'll look at in particular is prompt entropy, which is kind of a central link actually between these three families. And we show this with proofs in the paper, which I won't get into here, but it's pretty interesting that one metric can kind of unify these different ways of understanding your model. And you can kind of you can understand your model through the central lens of prompt entropy. And so what is prompt entropy? So entropy is capturing the compression level of the representations. So for any particular layer, we can measure what's called the effective rank of the D by D token covariance matrix. So this is, again, a bit technical, but just imagine that we have our covariance matrix of embedding, which should hopefully be a familiar matrix. Then we look at the eigenvalues of that matrix, and we take the Shannon entropy of those eigenvalues. So just a simple formula, but the implications of it are pretty impactful. So if our entropy here is high, that means our covariance has a high rank. The tokens, each row of the, or each dimension is like pretty unique, and the tokens are very spread out, and there's a lot of information in these embeddings. So this is meaning that there's a lot of information captured in the embeddings, and the model is extracting a lot of information from the prompt. So that's for a high entropy. But on the other end of at a low entropy, the covariance is very low rank, and you can say that the tokens are very compressed, and there's not a lot of unique information among the tokens. So we can measure this prompt entropy across the layers, just like we did earlier. So we'll visualize this again for the accuracies. And I'd like to take a moment and just linger on this graph and really dig into the details here. So we're showing these three different model families again. So let's start by looking at the Pythia model, which is the green line here. So this is again a next token prediction decoder only style model, just like GPTs. And let's start at layer 0 and go forward. So the first few layers have a high entropy. So the tokens are not compressed. There's a lot of information there. And then all of a sudden, around layer 5 or 6, which is around 20% depth for this model, there's a big drop in entropy, and all of a sudden it compresses a lot, and it stays pretty compressed for around 60% of the model, and then it decompresses at the end. So this is pretty shocking when we first saw this, because we understand how these models are trained. It's a pretty simple loss just to predict the next token. There's nothing in the loss function or the architecture that's telling it to do this, to have this intermediate compression. And one hypothesis for what's happening here is that the model is learning very abstract representations in the middle. And so it's taking this prompt and compressing it to something that's more abstract and more semantically meaningful. And so you can kind of think of the model as having three phases of information processing. So the first 5 or 6 layers where it's high at the beginning, there are some works that call this the detokenization phase, which is the model is converting from tokens to some kind of abstract language that the model understands. And then the middle is more of idea space, where you're no longer operating on tokens, but you're operating in concepts and ideas. And then at the very end, where it decompresses, some papers call this the retokenization phase, where the model is going from ideas, and because these are trained to output tokens, it needs to go back to tokens, which are more or less compressed, more information in the tokens. So that's one hypothesis for what's happening here. Another way to think about it is, if you're familiar with autoencoders, which are networks trained with an encoder and a decoder with some compressed latent space in the middle, it would kind of look like this, where there's some information bottleneck. So you can think of this decoder-only model, it's called, as implicitly, or emergently, I should say, learning a encoder-decoder model inside. So that you have the encoder phase, which is the first half, and the decoder phase, which is the second half. And recall that the middle layers are the highest performing layers on these models. So these more abstract, more compressed representations are what is actually being more performant on downstream tasks. So we just talked about the Pythia, so we can look at the other ones, which look quite a bit different. So BERT is also interesting. It's very flat along the way. There's no compression here. And we observe this across many different masked language modeling trained models. So this seems to be a property of that loss function. And Mamba is also interesting in that it's also trained with next token prediction like Pythia is, but because it's a state space model, which means it has linear attention instead of quadratic attention, each layer is doing simpler operations, it seems to not be able to compress early on, and the compression happens at the end. So each model family, and there's more model families than this, and I would assume that they would all have kind of unique fingerprints of internal behavior. Each model family has its own internal model dynamics that you don't really see unless you look inside. And it's just interesting and helps understand a little bit more about them. We can also look at this bottleneck, as I called it earlier, emerge during training. So here we have prompt entropy at different training checkpoints of the Pythia backbone. So Pythia is a really great model for doing this kind of analysis with because they released all of their training checkpoints alongside their model. So it's trained for 143,000 steps, and every 1,000 steps there's a training checkpoint. So I have here about 10 training checkpoints, and at the very initial step, it's a very light line, so it's a bit hard to see, but it's around the zero point 0.9 prompt entropy mark, and it's kind of flat across all the layers. And then as training happens, it slowly becomes more and more and more compressed in the middle. And it happens fairly quickly too. At around, I would say 20,000 steps, maybe 10 or 20,000 steps, it's already very apparent that this compression phase is happening. And kind of near the end of the model, like around 100,000 steps or so, it kind of gets to where it will end up and doesn't deviate much farther from that. And in the paper, we look at many different metrics and how they observed, how they change during training. And they all have interesting emergent behaviors like this, like just how you see it evolve over training. And again, nothing is, and the loss function is telling you this to occur. One last viewpoint we'll look at is bigger models lead to stronger compression in intermediate layers. So Pythia, alongside all of their training checkpoints, have many different scales. So they go from 14 million parameters. I think they go all the way up to like 7 billion parameters. But we show here from 14 million up to 1 billion. And we can see that it's very clear that the smaller models don't compress as much. And as you get larger, the models understand the prompts better and they compress the information much, much better. And this leads to better performance. The model scale helps as well, but these intermediate layers being more compressed also leads to better performance downstream. And there's also a good connection between a low entropy, which high compression, and high performance in autoregressive transformers specifically. So we don't see it as much with BERT or Mamba, but for Pythia, on the left graph where it's compressed and low, that corresponds to a peak in accuracy on the right graph. And we can measure this very rigorously. We looked at like Spearman rank correlations and all sorts of different correlation metrics. And yeah, it's a pretty clear, and the entropy is a good predictor of the downstream performance for these models. And this lets us do kind of a simple experiment, which is looking for free performance boosts in the model. So let's say our problem is we need to get better embeddings from our model, but we have no labeled data to train anything. So we have no labeled data to test like which layer is best on a classification task, for instance. One good solution is finding the layer with minimum entropy, because there's so much correlation between entropy and accuracy. So if you just do this simple solution, you can find on many tasks like a 5 to 10% performance improvement with no additional training. And so we look at this more rigorously in the paper as well, but we observe this not only in embedding tasks, but also in generation tasks as well, like if you're generating tokens from the intermediate layers. So this is a very general finding. And it's not just for language models, but it also works for vision models. So a big part of our paper as well was looking at how transferable these findings are to the vision domain. So in vision, there's like a very rich selection of models trained on many different pre-training tasks. So you have SemCLR, you have JEPA and MAE, you have DINO, which we talked about earlier, and also supervised models that are trained on classification labels. So we checked the vision modality to see, do intermediate layers still outperform final layers? And how does the different pretext tasks, pre-training tasks, affect the internal representations? Um, so like just like in language where we notice that autoregressive models compress in the middle, we also see that in vision, where autoregressive models are compressing in the middle and also peaking in performance in the middle. So there's this paper out of Apple called Autoregressive Image Modeling. They have a couple different versions now, but AIM, Autoregressive Model V1, has this very nice property of uh, minimum, or it compresses entropy in the middle. So around layer 10. So if you look at the left graph here, the blue line is this AIM model. So it stays flat at the beginning, just like we saw with Pythia. Then it compresses quite a bit, and then it slowly decompresses at the end. So this is very reminiscent of what we saw earlier with Pythia. Um, and I really like this graph because it shows alongside AIM, you have these other models like CLIP and DINO V2 and MAE. Each different pre-training task kind of has its own fingerprint for what's going on inside the model. And there's kind of, it looks like there's two striations of models. So you have like the top, so models that are around zero point 0.7 to 0.85 prompt entropy, and so like those kind of stay flat the whole time, and then you have models that are compressed the whole time, like AIM-V2 and um, the bird style thing, beat it's called. So the and then AIM V1 kind of goes between these two striations. And I will mention, so AIM V2, even though it's technically AIM, it's quite a bit different from AIM V1 in the sense that it's trained on the multimodal task with text, so it's not quite comparable to AIM V2. So in case you're wondering why AIM V2, this other autoregressive thing, looks different, the pre-training task is very different, so it's not comparable with AIM V1. Exactly. Um, so the key takeaway is that autoregressive training creates these beneficial bottlenecks across modalities. And we see on the right graph also that AIM is peaking around layer 15, and accuracy there is a few percent better than the last layer. So a little bit of performance boost there. So the key benefits of these intermediate layers. So it's very easy to get a nice performance boost. So you can get better embeddings with one line of code, just getting embeddings from the intermediate layer rather than the final layer. It's that simple. If you're using an intermediate layer, this means you can load less layers into your model memory, which means less inference time, less memory is required. Forward passes are much quicker. You can fit larger batches and so on. It also imparts a better understanding of internal model behavior, so you can understand more how the model is processing information across the layers, which is not a bad thing. Like these models are black boxes, so any understanding that we can get is very helpful. And there's already been follow-up work, which is not just observing pre-trained, not just observing these metrics in pre-trained models, but actually training models with these metrics. So you can optimize prompt entropy explicitly, and this was done in a follow-up work called seq-VCR, which improved math reasoning on the GSM-8K task. So like these prompt entropy metrics, it's not just for observing, you can train with them, and it helps quite a bit in preserving the information in intermediate layers. So we'll kind of just wrap up with some implications for these emergent phenomena and tie everything back together. So across the board, I would claim that these emergent properties, like so new capabilities or understanding model dynamics, it gives insights to the model black box. So like a lot of times, like you don't really understand, or it's not easy to understand what exactly is going on inside. You don't An off-the-shelf model might say it works for a particular task, but it's not advertised for this other task. So it's hard to know like where it's applicable. And I guess one message I would like leave is off-the-shelf models can be adapted and improved for a variety of tasks. As we saw with DINO, like it was trained like on this self-supervised loss, but it's applicable to so many different tasks, and just more and more are being discovered. And over the years, it was kind of a slow start with segmentation, and then they added depth estimation and so on. And now there's dozens of tasks explored in DINO v3. And it's also applicable to like other modalities, so you can apply these models to like understanding medical images or satellite images or non-RGB images and so on. It's just very strong features that are very general. And new and improved models are coming out all the time that can serve as drop-in replacements for these foundation models in your pipeline. So if you design your pipeline to be kind of abstract to the model, you can take advantage of these new models that are coming out, because capabilities won't be taken away. Like they'll only be added. So if something works in DINO v2, chances are it'll work in DINO v3 as well. And most likely it'll be better.